Okay, so here we have some limits that we are going to we're going to take the limit algebraically. So the strategy here, and I'm just going to write this out because I want to emphasize that this is a strategy that works when we're taking the limit as x goes to infinity or minus infinity. So strategy. So when we're taking the limit as x goes to plus or minus infinity of a rational function, so like the one that we have right here, then our strategy is going to be to divide the top and bottom of the fraction by the highest power of x in the denominator, or I'll just say the highest power in the denominator, because we may not always be using x as our variable, but the highest power of the variable that appears in the denominator. So in this case, the highest power is that x squared. So I'll write that here. So it is important to remember that this is in the denominator. So you're not looking at the numerator. Okay, so highest power in the denominator is x squared. So that means that we are going to divide 3x squared minus x minus 2 by x squared, and also, so this is our new numerator, and then also the denominator, so 5x squared plus 4x plus 1 over x squared. Okay, now I know it looks like we just made everything more complicated, but I promise you this will work out. So what we do now is we're going to split this into different fractions. So we'll split, we'll get 3x squared minus x over x squared minus 2 over x squared. And then in the denominator, we'll get 5x squared over x squared plus 4x over x squared plus 1 over x squared, right? Okay, now let's do some simplifying. So some of these powers of x will cancel. Like here, we'll just get 3, and then we'll get 1 over x minus 2 over x squared. That one stays the same. And then in the denominator, we get 5 plus 4 over x plus 1 over x squared. Okay, so now we have this. And the reason why we did this manipulation is because we know how to deal with limits like this one. So for instance, we know that the limit as x goes to infinity of 1 over x is equal to 0, and the limit as x goes to infinity of 1 over x squared is equal to 0. And that's by that fact that we talked about last time in the previous video. And then what we have, so for instance, if we have 4 over x, that's just multiplying by a constant, and we'll still get 0, right? And the same for this one. So if we can actually evaluate this limit using these facts, and we'll just get 3 minus 0 over 5 plus 0 plus 0. And I wrote it this way just to emphasize that we took the limit of each of these. I was using the division and addition and subtraction rules all at the same time, but that's fine. So I don't necessarily expect you to write all of that out anymore. Okay, so that is how we approach this type of problem. And so here's our answer. And now in this next example, this is not exactly a rational function because we have this square root. So a rational function is supposed to be a ratio of polynomials, but we actually just use the same strategy. So we can use the same strategy here. So the idea is, so the highest power in the denominator is just x. It's right here. Right, so we divide the top and the bottom of the fraction by x. So we'll get x squared plus 4x over x. And then we get 4x plus 1 over x. Okay. Now, in the denominator, this is going to work the same way as it did in the previous problem. In the numerator, I want to get the x inside of the square root so that I can do some cancellation. So in order to do that, I have to, so if I want to put x into the square root, I will have to square it, right? So I will get this over x squared now. And then in the denominator, we get 4x over x plus 1 over x. Ooh. Okay, so now we're going to do our we're going to split this fraction in the numerator. Okay, and we get 4 plus 1 over x in the denominator. And if we simplify a bit more, we get 1 plus 4 over x inside the square root. And then we know that the limit as, oh, I dropped my minus, so this is minus infinity, and this is minus infinity as well. Okay, but still, the limit as x goes to minus infinity of 1 over x is 0, and the same goes for 4 over x, because it's just a constant multiple of that. So what we get is the square root of 1 plus 0 over 4. And of course that is just 1/4. And that is our answer. Okay, so there's one more thing, or one more concept for this section, and that is, well, the book calls this infinite limit to infinity. That might sound kind of confusing, but the idea is just that we have the possibility of getting as, so as x goes to infinity, the function could approach infinity. So that would just mean that as the x values get larger, the function values get larger. So I guess I'll write that here. Okay, well, there are other like corresponding notions, so I'm not going to write out the interpretation of each of them, but it will be just a small variation of this idea. So hopefully it's clear. So we could also get the limit as x goes to minus infinity equals infinity, and that the limit as x goes to minus infinity equals minus infinity. Okay, and we're going to look at some examples of this. Okay, so first, the limit as x goes to infinity of e to the x, so our exponential function, which we were looking at the beginning, this we can see that as the x values get larger, our function values get very large because this grows very fast. So we get that this limit is equal to infinity. Okay? And then we get a similar thing if we look at the cubic function. So in this case, I'm going to leave some room. So our graph looks like this. This is x cubed. And we can see that the same thing happens where as x gets large, as we move out towards infinity, the function gets large. And so we can say from the graph that the limit is equal to infinity. And also, as x goes to minus infinity, the function gets very large and negative, so of x cubed is actually, so it goes to minus infinity. Okay. Oops. Okay. There we go. Okay, and so we'll do one more example. So this is the limit as x goes to infinity of x squared minus x. Now, so you might want to say that, okay, as x squared, as x goes to infinity, x squared gets very large, and as x goes to infinity, obviously x gets very large, so we get infinity minus infinity. But the problem there is that this is not well defined. And it's actually what is called an indeterminate form. We're not going to talk about them right now. We are going to talk about them later in this class. But there is another way of dealing with this. So we don't want to get infinity minus infinity because that's not something that's well defined. Infinity doesn't behave nicely when we try to do this. So what we can do is be a little bit clever with our algebra and factor this as x times x minus 1. Now, as x gets large, obviously this x gets large. So does x minus 1. It's right behind x. It's just 1 less than x. So as we get out to, say, like 1,000,000, if we subtract 1 from that, it's basically of the same magnitude. It's very close. So these are both going to get very, very large, and their product is going to get large. Therefore, this will actually be equal to infinity. So does x minus 1, and so does the product x times x minus 1. So it's safe when we have something that is very large, so as x is getting larger, and we multiply it by something that just makes it even larger, then it's safe to say that we still get infinity. But if we have some kind of cancellation, then it's not clear. Okay, and then one more thing I wanted to mention is that if we get, so if we get that the limit to plus or minus infinity. So this is just like a shorthand way of writing is equal to plus or minus infinity. This is a shorthand way of writing any of these situations. So if we get this, we do not get a horizontal asymptote. So remember that in our definition for horizontal asymptote, I said that L that it was approaching, it had to be a finite number. So if we do get infinity, that doesn't mean we have a horizontal asymptote. And you can kind of see, like if you were to look at these graphs, you wouldn't say that x cubed has a horizontal asymptote at infinity, right? So, okay, it doesn't give a horizontal asymptote. Okay, but it could be the case that you have on one side that your function is approaching infinity, and on the other side it's approaching a finite number, and then you get a horizontal asymptote. In that case, it's just coming from the other side of the graph. So in this is an example of that, right? We have a horizontal asymptote at 0, and then on the other side of the function, it's escaping to infinity. Okay, so if you're asked to just determine the horizontal asymptotes of a function, all you need to do is take the limit as x goes to infinity and also the limit as x goes to minus infinity. So we just compute this here. And we use that strategy we talked about before. So the highest power in the denominator is x cubed. So I'm going to divide the top and bottom by that. And we get 2x squared plus 1 over x cubed. And then we get 3x cubed minus 5 over x cubed. And I'm going to just simplify this a bit faster than I was in the previous examples. So we get that for our numerator, we get 3 minus 5 over x cubed in the denominator. And then as x goes to infinity, this guy, the 5 over x cubed will go to 0, 1 over x cubed will go to 0, 2 over x will go to 0, and so the only thing that doesn't go to 0 is that 3. So we get 0 plus 0 over 3 plus 0, and that's just equal to 0. Okay. So that means that we get a horizontal asymptote at 0. Okay, and it turns out that the computation for the limit as x goes to minus infinity is actually going to be exactly the same. So we also get 0. And so we have one horizontal asymptote at y equals 0. Okay, so that's all for this section, and don't forget to answer the comprehension check question.